You ever stop and wonder what actually holds our world together? I'm not just talking about big stuff like bridges and buildings, but the machines we use, every single day. Well, in this explainer, we're going to peel back the metal and look at the invisible architecture, these really elegant principles of force that stop everything from just flying apart. Let's dive in.
Okay, let's take your car engine, for example. It's basically just a series of controlled explosions happening over and over again, thousands every single minute. That's an incredible amount of force. So what's stopping the whole thing from just tearing itself apart? Well, it's not just about using super strong metal. It's about a really deep, kind of elegant understanding of balance.
And that right there brings us to our first big idea, static equilibrium. Honestly, this is the bedrock principle that engineers use to tame and control all those insane forces. So, what is it exactly? Well, to put it simply, an object is in static equilibrium when it's perfectly still. And why is it still? Because every single push, every pull, every twist acting on it completely cancels each other out. Think of a perfect game of tug-of-war, where nobody moves an inch. That perfect, motionless balance, that's static equilibrium.
But here's the thing. For an engineer, this isn't just some abstract concept. It's a set of really strict mathematical laws. You can see the equations right here. For anything to be in equilibrium, the sum of all the forces in any direction, up, down, left, right, it all has to add up to 0. And the same goes for all the twisting forces, what we call torques. They have to be 0 too. If even one of these isn't balanced, well, that's when things start to move and, usually break.
Okay, so how do engineers take this idea and apply it to something super complex, like a real machine? Well, they've got this brilliant method. They break it all down and analyze each little piece using just 2 simple golden rules.
So here's the trick. Pretty much every single component in a static machine can be simplified into one of 2 types. You've got a part with forces acting on it at only 2 points, and you've got a part with forces acting at 3 points. That's it. And if we can get our heads around these 2 simple cases, we can basically analyze almost any complex structure out there.
All right, let's start with the first one, the 2-force member. Just picture a single link in a chain being pulled from both ends. For that link to stay perfectly still, the forces have to be balanced in a very specific way. They have to be equal in strength, they have to be acting right along the same line, and they've got to be pointing in opposite directions. It sounds simple, right? But it's an incredibly powerful rule.
Okay, next up, the 3-force member. This one's a little more complex, but it still follows a couple of really elegant rules. So, rule number 1. As you can see in this diagram, the lines of action for all 3 forces absolutely must all cross at a single point. Engineers call this the point of concurrency. So why is that so important? Well, because if they didn't, those forces would create a twist, a torque, and the whole thing would just start spinning.
And the second rule? This one gives us this really neat visual proof that everything's in balance. If you draw each force as an arrow, where the length of the arrow shows how strong it is, and then you place them tip to tail just like you see here, they have to form a closed triangle. It's a perfect loop. This shows visually that all the pushes and pulls have completely canceled each other out. You end up right back where you started. No net effect.
Okay, so we've got the rules of the game. Now for the really fun part. Let's actually use them to solve a puzzle. We're going to deconstruct a machine and find the hidden forces that are holding it all together.
Now to do this, engineers have a super important tool. It's called a free body diagram. The best way to think about it is like creating a most wanted poster, but for forces. You basically isolate one single part of the machine, pull it out, and draw only the forces that are acting directly on it. It just clears away all the noise and lets you focus on one piece of the puzzle at a time.
So here's our puzzle for today, a classic 4-bar mechanism. We've got one known culprit, right? This external force F that's pushing on link 4. But for the whole system to stay in balance, there have to be 2 other hidden forces involved, one from link 3 and one from the ground, which is link 1. Our mission, should we choose to accept it, is to figure out what those hidden forces are.
So here's how we're going to solve it, step by step. First, we isolate link 4. That's our free body diagram. Second, we figure out what we already know. We know everything about force F, and we know the line of action for the force coming from link 3. Okay, third step. We apply our rule, we just extend the lines from those 2 forces until they cross, and bam, that's our point of concurrency. And because we know all 3 forces have to meet at that point, we now know the direction of our last mystery force. So for the final step, we've got one force completely figured out and the directions of the other two. We can now draw our closed force triangle and find the final answer.
And there it is. See? By finishing that triangle, we can now just measure the other two sides, and that gives us the exact strength and direction of those hidden forces. It's pretty amazing, right? We've just used some simple geometry to make the invisible visible. That is the power of static analysis.
But what happens when things aren't static? I mean, most machines move, right? And with movement, you get fluctuating energy. So how in the world do engineers manage all those peaks and valleys? Well, this brings us to another brilliant piece of this invisible architecture. Let's go back to that car engine we were talking about. In a 4-stroke cycle, you only get one single powerful energy burst. That's the power stroke. The other 3 strokes, intake, compression, exhaust, they actually use up energy. So you got to ask, how does the engine push through those dead zones without just grinding to a halt?
The answer, my friends, is the flywheel. The easiest way to think of it is like an energy bank account. During that power stroke, when there's way more energy than needed, the flywheel absorbs that surplus and stores it as rotational momentum. It's like making a deposit. Then, during those other strokes when the engine is running an energy deficit, the flywheel makes a withdrawal, releasing that stored energy back into the system to keep the whole thing spinning smoothly.
Now, it's really easy to confuse a flywheel with something called a governor, but they do totally different jobs. A flywheel, like we see here, is all about smoothing out the energy ups and downs within one single cycle. A governor, on the other hand, manages the average speed over many cycles, usually by messing with the fuel supply. Here's a good way to think about it. The flywheel manages the rhythm while the governor sets the overall tempo. And this is really the key thing to remember. A flywheel's job isn't to keep the speed perfectly 100% constant. That's not what it does. Its whole purpose is to be a buffer. It soaks up the harshest energy spikes, and then it fills in the deepest energy valleys. It basically transforms this jerky, inconsistent power delivery into a much smoother, much more useful output. So from the perfect balance of static equilibrium all the way to the energy-smoothing power of the flywheel, we've seen how these really elegant, simple rules allow machines to master just incredible forces. So the next time you see a bridge or a crane or even just look at an engine, look a little closer. Ask yourself, what invisible forces are locked in that perfect tug of war right now? What unseen energy is being banked and spent? Because trust me, once you start looking for it, you'll start to see this invisible architecture absolutely everywhere.